Surya, and I've been in this IT industry for almost 10 years now. Now, the main agenda for today's session here would be, we will be discussing on why not the feed-forward networks, why we should not go ahead, and again, why not you use the feed-forward networks, what exactly is recurrent neural networks, what are the issues faced with recurrent neural networks, what exactly is the concept of vanishing and exploding gradients, how to overcome these challenges, and then we'll be discussing on long short-term memory units. And at last, we'll be discussing on the same use case for long short-term memory units itself as a part of today's agenda for today's session here. And the last 15 to 20 minutes, we'll be discussing on the entire training that we have to offer as a part of certification course that we have to offer that will help you in upgrading your skill set and then taking your career to the multiple leaps, right? So now let's get started. Now, let's first of all understand why not feed networks, why not feed forward networks, why not, right? So again, there are limitations, there are obviously limitations to these networks here, right? And again, let's understand what exactly are the limitations here and why not we spatially use this. Now, the feed forward network that we know of, that we are aware of, again, can be exposed to any random collection of photographs, right? And the first photograph it is exposed to will not necessarily alter how it classifies the second, right? Now, for example, suppose as part of a machine learning, what we are trying to do, we are simply trying to feed. Now, we are simply suppose trying to feed the entire system with the image of a baby elephant here, right? Again, the same output is also again in terms of any puppy or any dog picture, right? Now, obviously, there is no relation between the elephant and the dog, right? And that's why seeing a photograph of dog will not lead the net to perceive an elephant next, because again, they are not correlated, and that's why this will not be functional out there, right? Now, as the same example, suppose whenever we are reading a book, you understand it based on your understanding of previous words, right? So based on what kind of vocabulary that we have here, right? What kind of words that we have been familiar with? What kind of words that's present here exactly as per understanding, right? That's how we read books, right? That's how we are able to read books. We are able to visualize it and then get started, right? But again, even though we have a good understanding of the entire feeds and entire previous words, right? Still, we cannot predict the next word in a sentence if we use the feed forward next, because again, this is based on the previous understanding, right? So again, suppose input is also given as t plus 1 here, right? So our output can be again as t minus 2, t minus 1, and t. Again, these are all are independent of the previous outputs, right? And that's why it cannot predict this, right? Using the feed forward network, we cannot predict what should be the next word as well as a part of limitation offered under feed forward networks that we know of, right? And again, a simple way to how to overcome this challenge here. First of all, now here we can use the recurring network here. Now here we can use the concept of RNN. Recurring neural network is commonly referred as RNN, right? That will be using multiple times here. So RNN is simply, now what exactly the RNN is? First of all, let's understand this using a simple layman terms here. First of all, as a simple example, first day we did the shoulder exercises. The second day we are doing biceps. On third day we are doing cardio, right? And then based on this particular input here, we can predict the type of exercise here, right? Suppose first of all here we have days of the week, right? Now based on days of the week, we can do shoulder, we can do biceps, and we can do cardio as well. They are all three possibilities, right? And then based on the month of the year, again on that particular month, again we can have shoulder, again we can have biceps, again we can have cardio. Same way on health status, again we can do shoulder, we can do biceps, or we can do cardio, right? Using the feed forward network, this is how the entire network, the entire algorithm for feed forward network is based on, right? And again, using the recurring network here, what we can do, if we did shoulder yesterday, then obviously we know if we did shoulder yesterday, then today we have to do biceps, right? If we did biceps yesterday, it doesn't matter which kind of like which day of the month it is, which day of the year it is, right? If we did biceps yesterday, then we have to do cardio today, right? If we did cardio yesterday, now we have to do shoulder exercise today here as a part of recurring network here, right? And same way, suppose let's say we predicted shoulder yesterday, again we can do biceps today itself, right? If we predicted biceps yesterday, then again today is the day for cardio. Again, if we predicted cardio yesterday, then today is the day of shoulders, right? Again, if we actually did these exercises, again these are the actual number of exercises that we can do in a given day here as a part of recurrent network, right? And that's why, again, information from any prediction at time t minus 1, again, this can also be a part of the prediction plus the new information, and then this can be prediction at time t, whatever needs to be done here, right? And that's why this is a part of, and that's why this entire setup here is called as a recurrent network, here. Now, we also have to work on training a recurrent neural network here, right? Now, as you know, recurrent neural network uses a backpropagation algorithm, right? And again, but is it what? It is applied for every timestamp. Again, that's why it is called as a backpropagation through time, called as BTTT. So this is a common abbreviation that will be getting used to as we continue further in our machine learning algorithm, right? So this here is called as a back propagation through time, called as BTT, right? But now again, let's also look at the multiple drawbacks and issues with back propagation. First of all, here we have the vanishing gradient, and then we have exploding gradient here. Now let's understand these, what exactly these are one by one. Now, when we talk about the vanishing gradient problem here, so basically it is based on, again, on a simple logic, right? So when we talk about a vanishing gradient model, it is simply based on simple understanding that, again, if a small change is introduced in the data system, then that means a small change in the parameter value, right, will simply affect the entire network's output here as a part of the vanishing gradient problem here, right? And that's what we can see. If the change here is too small here, if the change here is too small here, again, it will now the entire system will fail to understand and learn what exactly the changes has been as a part of the vanishing gradient problem here. So basically, whenever a change in the parameter is we can say exactly the parameter value again causes very small changes, right? So if there are very small changes made by the parameters value, again the network cannot learn the parameter effectively, and that is the problem faced in vanishing gradient as a part of the vanishing gradient problem. All right. And same way in exploding gradient, again, if the output is too large here, again, it can also not be understood and again, well integrated by the entire system here as a part of backpropagation algorithm, right? And that's why if the value is too large, again, that will also be a problem. Again, the value is, if it is too less, again, it will also be a problem in terms of vanishing gradient, right? And that's why we do now, that's why these both are the drawbacks. These both are the drawbacks, right? These are the drawbacks of the back propagation model here. All right. Now let's see how we can overcome with these challenges here. First of all, let's understand how we can overcome vanishing and exploding gradient problem in both the cases. So first of all, if we are talking about exploding gradients here, again, instead of starting back propagation at the last last timestamp, what we can do, we can simply choose a smaller timestamp. Like for example, we can choose a small timestamp like we have 10, right? Because again, we'll lose all the temporal context after 10 minutes stamps here as a part of the truncated back propagation model here, right? Same way we can go for clip gradients at threshold. Again, we can clip the gradients when it goes higher than a threshold. We can do that to avoid these kind of challenges, right? And same way in vanishing gradient, again, we can simply use activation function that we have RLU. We have now which can simply give which can simply give output one when calculating gradients, right? We can again do the same thing for RMS prop as well. we can simply clip the gradient when it goes higher than the threshold. And again, same here, we can also use LSTM and GRUs, where we can use where we can simply use it for different network architecture, right? That has been spatially designed with use to combat this problem here, right? So these are specific and unique architecture that we can use to solve the issue as a part of vanishing gradient here. And next, as a part of a long short-term memory network, these are commonly abbreviated as LSTMs, right? And these are special kinds of RNN as a recurrent neural network. Now, basically, they are used for their long-term dependencies capacity, right? That's why we use long short-term memory networks, right? And again, the repeating model in standard RNN, again, this is a schematic diagram of how exactly it works here. Now, as you know, the first step in any neural network, in suppose if you talk about the long short term memory management here, right? Memory networks. Now, the first step in any LSTM is basically first of all to identify, right? To identify that piece of information that is not required, and again will be thrown away from the cell state as a part of cleansing of data, right? And this entire decision is made by a sigmoid layer called a forget gate layer. This is what is called for forget gate layer here, right? So for example, here if we have the weight, here we have the output from previous timestamp. If we have the new input and then we have the bias, then we can use this formula for the LSTM. We can do that. So here we need as simple as weight. Here we also need the output from previous timestamp. Here we need the new inputs and the bias from our end, right? So, and this is how the formula is structured here to get started. And as a next step here, again, we can have to decide what kind of information we are going to store in the stealth state, right? Again, we can discard. We also will be discarding the unused piece of information, right? And then we have to decide what kind of information we want to store there. And this entire process of, again, comprises of multiple steps. First of all, here we have something called as a sigmoid layer, right? So sigmoid layer is simply called the input gate layer, and basically it decides which values will be updated, right? And next we have a tan layer. Again, it simply creates a vector of new candidate values that can be added to the state here, right? And again, here we can see again how we can calculate the sigmoid layer here and the tan layer. Now, same way like we are discussing on the long short-term memory here, now we can simply discuss a simple use cases here. For example, suppose when we simply arrange any of our calendars, right? Again, we simply prioritize now. Suppose if we have multiple appointments throughout the entire day, we have multiple chores to take care of. Again, we have multiple meetings to take care of, right? We can fix appointments. We can prioritize based on the priority level. We can do that, right? And again, if we need again, in case we need to make some places for anything important, we can know now. We have to know like which meeting can be cancelled. Again, which can or where we have a possibility of canceling which meeting and how we can accommodate and how we can adjust those changes accordingly, right? So again, if we want to know, okay, which of these meetings can be cancelled, again, we have to know which one has the highest possibility of being cancelled or which can be cancelled, which can be adjusted, and how we can use and how we can adjust those accordingly. We can do that, right? And again, based on the recurrent neural network, again, it doesn't do in that particular sequence here, right? And again, in order to add new information, basically what it will do, it will simply transform the existing information completely by applying a function here, because that's the main concept of using the RNN, right? And again, because of this itself, the entire information is modified, because again, we don't want to lose out on the integrity here, right? As a use case, we don't want to lose out on the integrity of the model here, and that's why we can simply losing out on the entire integrity of the model here, right? Which we definitely do not want, correct? And again, that's why now once the entire information is modified because of this reason, again, there's no consideration left to make, right? And but if we are using the same concept of long short-term memory here, again, we can simply make small modifications to the entire information, right? By multiplications, we can use multiplications and additions for doing that, right? Because when we are talking about the long short-term memory here, the entire information, again, it simply flows through a mechanism, right? It simply flows through a mechanism which we call as a cell stage that we discussed, right? And again, when we are following this mechanism here, again we can selectively remember, or again we can forget things, so that the entire data or entire architecture does not need to be changed, just like it happens in recurring networks here, right? And since we are dividing this, since we are simply dividing, since we are structuring the entire information flow in the format of the cell states, right? Then what we can do with the information at a particular cell state can have multiple dependencies. We can have multiple dependencies based on these different cell states here, right? First of all, again, we can simply make sure the entire trend that has been following, again, it may be a downtrend or there can be a simple uptrend as well. We can do that, right? Or for example, suppose now let's take the example of simple, suppose let's say we are talking about the stock prices, right? Suppose let's say we are talking about prediction of stock prices, here, right? So based on whatever we had discussed, now if we are going for prediction of stock prices here, and that too for a specific stock here, right? Now, if we are talking about on which factor this entire stock price will depend upon, again, they will be dependent upon, suppose we can say, it will be dependent upon the previous stock that we discussed here. First of all, it will depend upon the stock price on the suppose stock price on the previous day, on the previous day itself, as a first option, right? Again, it can be a trend as well. It can be a trend on the previous day. That means, again, suppose trend on the previous day itself, on the previous day itself. Now it can be, now suppose it can be downgraded, or it can be down, or it can be up and running as up as well. So depending upon, suppose we had seen a huge drop in the prices here in the previous days, again the same trend can be followed, or again suppose there has been a price increasing in the last day, they can be increased as well in the subsequent days as well. All right. Or suppose there has been some, and again some, for example, there has been change in policies, or introduction of, we can say, change in policies, or it can be introduction of new factors. For example, suppose there has been change in government policies, there have been introduction of new stocks here. Again, that can also impact the entire stock prices here, right? And that's why we here discuss the concept of cell states here. It will simply depend upon the previous cell state. And again, it can also depend upon the hidden state as well. That means the output of the previous state. And again, that can also be dependent upon the input at the current time step. That means, again, that is a current moment or whatever is happening to that particular stock as in a real-time scenario to solve this entire issue here. Okay, let me show you a small example here to make these things pretty much clear. Just a moment. Let us fetch a small example to have a better clarity on top of it. Just a moment. Let's pull one of our libraries that we had designed in. Now, a simple example, now let's do one thing. Let's open up our PyCharm to simply create something inside the library here. So let's do one thing. Let's simply go back to a PyCharm. So PyCharm is one of the libraries here that we can use. PyCharm is one of the IDs that we can use for coding on top of Python, which is one of the most popular IDs available out here, right? Although we can use other libraries as well. We can use IntelliJ, we can use Visual Studio, we can use any other code editors as per the requirement. But again, PyCharm is the most popular ID, especially for writing codes on top of Python, right? Now let's do one thing. Let's remove this one here. Now to get started here, what we can do, we can simply first of all import multiple libraries here. So now here we can simply import, now from the pandas library here we can simply import, the pandas libraries. And again, here from pandas we can import the data frame from suppose from Keras library here. Keras, now again we want to focus on models here. So here we can import sequential. We can import sequential here. And same way from again from another part from other suppose same way from Keras we can again from Keras layers we can import dense as well, and then from Keras again from Keras we can again import LSTM as a part of our example here. Import LSTM. Now, for example, suppose our entire focus here, suppose let's say we want to simply define the binary encode on input patterns here, right? Suppose we want to simply return a list of binary vectors here, right? So suppose list of binary vectors, we can add a binary vectors just to avoid confusion. We're adding a comment here, right? Suppose here we can define the encoding here. Here we can define the encode. Again, here we can set the pattern as well, like pattern again, and here we can define the pattern as suppose NN unique. It should be N unique here, and then here we can simply now in encoded we can define the list that we are trying to create here. So we can define the entire list, and then from listed, so now here we can find the value here, right? So for example, so for value in pattern, we can define. Now for value in pattern, we can define the logic. Suppose in a given row here, we want in a given row, suppose let's say we want to start with 0 in x for any value as x. Now here it can be in any range here, and our range should be what? J should be same and unique that we had already defined here, correct? So it should be n unique, correct? And then under row, now again we can simply focus on the row here, and again we can define the value as a row as the index value here, right? And again we can now for this one we can define the index value as 10. We can define it, and then we can simply encode and append it. We can simply append the entire row that we have currently created, right? And then we can simply return the encoded, right? And same way, suppose again, if you want to create the input output of the whatever vectors we have encoded here, we want to create the input output here, right? The same way, suppose, okay, let me just add a comment here so that it will be much clearer for everyone. So here we can name this as suppose create input output of vectors, here, right? Now for creating the input output here, again we can define it. Suppose let's say we are simply define suppose to xy, right? So again for to xy to suppose let's say we can name this as to xy pairs. Again we want to use the encoded, right? So again we can make sure this as encoded here. Now here we can define the logic here. For example, for I in range, right? Whenever we're defining here for I in range, and then we can define the starting value here, and then we can define the length of the code that we will be focusing on, right? So again, here we can define the length of the code that will be returned here, right? So here we can define the len here. Now again we can define suppose now here we want to append x here, right? So again here we can append x, and then we can define the index value here, and in the index we can define encoded, and then we can define suppose I and -1 as logic here. The same way we can also append y, because here we are trying to append both here. So again we can do the same thing here. We can again append it again in same way in encoded, and then we can define I, and now we can return x and y both. We can return x and y. And suppose we want to convert the entire sequence. We want to convert the entire sequence to xy pairs, right? Suppose here we can do that. Suppose if you want to convert x and y for the LSTM here, then we can do that easily, right? So again, we can define now here again for doing that, we can simply define it, right? We can simply now here for doing that, we can again simply define it, right? So again, if we can define this, suppose to now here we can mention as to LSTM, and again it can suppose the entire data set here. Now here we have to define the sequence that we have currently created here, the sequence, right? So now here it can be the entire sequence that we want, and now this can be again the same and unique that we had declared earlier, right? Now for this one, again we can use encode. Now here we can define the, now here we can call encoded here, and then here we can encode the same sequence, and then we can define this for n unique. All right, and then here we can define now, and then here we can define in xy, we can define this. Suppose again we can define this to suppose same to xy pairs, because here the main goal is to convert the x and y, right? So here we are simply, our main goal is to convert the xy pairs itself, right? So here we are converting this to xy pairs again for the encoded here. So now here let me add a simple tag here so that it becomes clear for everyone. So again here simply hot encoding here when we define encode, and again this part here, now what we are using this one for, we're simply using this for converting the in-out patterns, right? Converting the in-out patterns. This is not a comment here, right? Again, so now if we want to convert, suppose say we want to convert to LSTM here, right? Then we can simply, now here we can simply define the fx value here, and same way for y here. Right, now here we can define the data frame. That's why we have used the data frame library here. So here we can define the data frame here. Now, and in data frame here we can refer data frame for y as well, data frame for x, and data frame for y. And then here we can use the LSTMX. Here we can define the x values. Same way here we can use LSTMX again. And in here we can use LSTMX, and then we can use the reshape. The reshape, because again here we are trying to simply reshape it as a part LSTMX. Again, then we can shape it to the index value of 0. And now let's simply shape it to the first value as a part of index. And now we can simply define the same thing for LSTM for y. Again, we can define the value for LSTM for the y, and then we can simply return the LSTMX and LSTM y. We can do that. Now suppose, now obviously when we are defining these, again we also need to define the sequences here as well, right? So again here we have to define sequence, here we have to define sequence as a part of example. Here we need to define a sequence, then only it will make sense, right? So then only we can start testing as well, right? So here we can define sequence here, whatever we had to call it. So here we have, suppose here we have sequence as 3, suppose we have 0, suppose here 1, we have suppose 2 and 4 as a part of sequence 1. And suppose in sequence 2 we can have suppose 5, here we can have 9, here we can have suppose 3, and again 2 and 1. Then we can define the LSTM as well. Once we are done here, we can define the LSTM here as well. Suppose we want n neurons. Suppose we want this to be at 20, right? Again, we want the batch as well. Again, we have to find the one batch here. Now, batch we want to keep it to 1. And then suppose same we have epoch. Suppose here we suppose here we keep it at suppose 220. And the features here, is simply the n features that we referred here. Again, it is equal to the n unique that we have declared earlier. And now simply to create the LSTM here, we can simply define the model as well. Here we can define the model as, suppose here we can call it as sequential, and then here we can define model add. Here we can refer to as suppose as LSTM that we defined here. Again, now here we can refer to whatever we had declared here, n neuron, batch, and epoch, right? So here, first of all, here it will be n neuron, then it can be batch input, and then it can be shape, and now and input shape here should be n batch, and then it should be 1, and then it should be features, right? To what we defined here. So here, first of all, it should be n batch, then it should be 1, and then it should be n features. And then in stateful, here we can define this as true, being the true in terms of stateful. Now we can define the model for suppose for add here. Again, it can be dense, it can be n unique. Again, here we can focus on the activation here. The activation should be supposed same way as sigmoid, right? So again, activation here can be a complete sigmoid here. Now we don't want curly braces here, we can keep it to normal. And at last, we can simply define the model, and then we can simply compile it. Compile at the suppose loss of a now here we can mention suppose as binary and cross entropy. And the optimizer here we can set it to Adam. Suppose here we can define the any user here, as you know, any user here, suppose. And same way here we can define the SQN. Suppose same way here we can test the LSTM here on multiple sequences here. Suppose our main goal is to simply test LSTM here, right? So okay, suppose we want to test LSTM on sequence 1 here. That we define here as sequence 1, right? So again, for doing that, we can simply print it. So here we can simply print sequence 1. And then in result section here, we can simply define the model, and then we can predict. Now here in terms of the model here, we can simply predict the classes, right? And here we can define a sequence for X. This has to be sequence for which sequence that we are simply testing here. It is the 1, right? So here we can define a sequence here, then we can define the batch size. The batch size, what should be the batch size that we are focusing on? So it should be supposed simply as n batch to what we had declared, and here it should be verbase. Verbase here we are simply setting it to 0. And at the end here we can also do the same model reset here. We can simply do the reset for the models here. We can reset the states, we can do that. And then we can define the condition. Suppose here we want it for I in the range, for the length and the results. In the result section here, it should simply print again whatever we define for X here. Suppose X, again the modulus here, right? It should not be X again. If no, this should not be equal here. If now again here, if suppose here we can define the condition here, if X is also not equal, right? And again here we can define the condition for y hat as well. And here we can simply attach it here and here. And now if we want here, we can simply attach it. We can attach it suppose to sequence 1. Suppose here we can define to the sequence 1 and again the index value here. We can also test it for sequence 1 and the I plus 1 as index value. And then we can define this for result as well. Result was again for I here. So same thing we can also do for sequence 2, and multiple other sequences as a part of LSTM here. So I guess it's almost time now, guys. So let's say we wrap it up for today. So thank you so much for joining, guys, and have a great day ahead. Take care. Bye-bye.